In this portion of Chapter 18, we're going to talk about the solubility of inorganic salts. So for example, calcium carbonate, that's what makes up chalk. When you put some of this in water, here, let me show you here. Here's some water. I'm going to take a piece of chalk and throw it in there. The chalk doesn't dissolve, or at least it doesn't look like it. And that's because for the most part, the calcium carbonate stays solid. But a little bit of it does actually dissolve. So you get a little bit of calcium ions that have dissolved in the water, and you're going to end up getting some carbonate dissolved in the water as well. It's not much, but it is there. And there is a, we can write this as an equilibrium constant, right? So we can write KEQ. That's going to be the concentration of calcium when a certain amount of it dissolves in water and it no longer dissolves, and a concentration of carbonate that dissolves to a point and then stops once it reaches some particular equilibrium value. This is the basic idea that we're going to be covering in this particular portion of the chapter. When we write these particular equilibrium constants, you'll often see them listed as K with a subscript SP, which stands for solubility product. And we're just going to start off by doing a couple of problems. Okay, the first problem is the KSP for silver chloride is 1.8 times 10 to the negative 10. Calculate the solubility of silver chloride in water in units of grams per liter. I better pay attention to that. Grams per liter. Okay, so I'm going to write the solubility expression. So I have silver chloride solid, and that's going to dissolve a little bit. We're going to get aqueous silver ion, and we're going to get aqueous chloride ion. And if I was going to write the equilibrium constant for this, which we're going to call KSP, that's going to be the concentration of silver at equilibrium, and it's also going to be the concentration of chloride at equilibrium. Notice we don't divide by solid silver chloride because we don't include solids in the equilibrium expression. Okay, so how are we going to do this? Well, like we do any other equilibrium problem, I've got silver chloride going to silver ion and chloride ion. We assume some initial condition. There's going to be a change that happens that brings us to equilibrium. We're not going to worry about the solid. We're going to assume we start with no silver dissolved and no chloride dissolved. We of course know that we're going to gain a certain amount to get us to equilibrium. We'll call that value x, and from the stoichiometry we can see it's 1 to 1. So we're going to have x amount of silver ion present at equilibrium and x amount of chloride ion present at equilibrium. So let's see, KSP, that's going to be the silver concentration at equilibrium, which is x. We're going to multiply that by the chloride concentration at equilibrium, which is also x. So I can simply write x squared is 1.8 times 10 to the negative 10. That's the value for KSP. Well, that's easy to solve. I'm just going to take the square root of both sides of this. And so 1.8 times 10 to the negative 10. Let's take the square root of that. And I get 1.34 times 10 to the negative 5. That's units of molarity. Remember, we get molarities when we're doing equilibrium problems. Well, molarity has units of moles per liter. The question asks for the solubility in grams per liter. So there's going to be another step here that we have to take. We're going to take 1.34 times 10 to the negative 5 moles of silver chloride for every liter. And let's see, what's silver? That's 107, isn't it? Hey Siri, what's the molar mass of silver? It's 108. So let's see, silver is 108, and then chlorine is 35.5. We add those together, and we get 143.5 grams per mole. If my math is good, 1 mole is 143.5 grams. So now we just multiply these together, and we'll have our solubility of silver chloride in units of gram per liter. 1.34 times 10 to the negative 5, and we're going to multiply that by 143.5, so it's like 0.0019. 0.0019 grams of silver chloride is going to be dissolved in every liter. Did I do that right? 1, 2, 3. Yep. Okay, so you know where I am. I'm on the Chapter 18B PowerPoint, and I have skipped to problem number 3 on slide 3 of the PowerPoint. I left problem number 2 for you to do. In this question, we're going to find KSP for silver phosphate. So we're not going to find it. We're going to find the solubility of silver in a solution of water that's been saturated with silver phosphate. We're given KSP for silver phosphate here. This is one of those cases where you better know your polyatomic ions, and you ought to know how silver phosphate dissolves when it does so in water. So I'm going to draw that out here. We have solid silver phosphate, and I know that that's going to dissociate into 3 silver ions and a single phosphate ion. I know that for a number of reasons. I know that because I have my polyatomic ions memorized. I recognize phosphate here, and I know phosphate has a -3 charge. The other thing that I notice is that there are 3 silvers, and I happen to remember that silver ions always form +1. These are all little clues to help you figure out how to see the dissociation of these things. Being able to do this is really important with these problems. So if you're struggling to see what I'm doing here, go back and look at your polyatomic ions again, and maybe spend some time rememorizing them and becoming a little bit more fluent in their definitions and their structures and their charges as well. All right, we're going to treat this like any equilibrium problem. There's an initial condition with some change that'll bring us to equilibrium. I'm not going to worry about the solid. Let's see, initially we're going to assume we don't have any dissolved. We're going to have to get a little bit dissolved. It won't be much because K is really small, so this won't move in this direction very much, but it will move in that direction. The change, notice, for every X amount of phosphate that I gain, I'm going to gain 3 times the amount of silver. I hope you see that from the reaction stoichiometry. That means at equilibrium, I'll have 3X silver and X phosphate. So let's see, KSP, how am I going to write that? Well, that's going to be the concentration of silver cubed times the concentration of phosphate. And of course, this only applies under equilibrium conditions if we're looking for, at the equilibrium constant. So that means that 3x, that's my equilibrium concentration of silver, and I'm going to have to cube that. You really need to pay attention here. And then we're going to multiply that by the equilibrium concentration of phosphate, which is x. Now, what is 3x cubed? A lot of you are going to say that that's 9x cubed. And what you're forgetting is that 3 cubed is 3 times 3 times 3, which is 27. So this is actually equal to 27, 3 times 3 times 3, times x to the 4th. And this value is going to be equal to KSP, which is 2.8 times 10 to the negative 18. A lot of mathematical steps there. They're not hard, but you just got to pay attention. So let's see. I have 27x to the 4th power. That's going to be 2.8 times 10 to the negative 18. I'm going to divide both sides of this by 27. So I have x to the 4th. That's going to be 2.8 times 10 to the negative 18. And I'm going to divide that by 27. Now I'm going to take the 4th root of both sides to get rid of this x to the 4th. So let's see, how am I going to do this in my calculator? I'm going to take 2.8 times 10 to the negative 18. I'll divide that by 27. Well, the 4th root is the same thing as taking the square root twice, so I could do that. I'll just take the square root twice in this case. I'm going to just take the square root, and I'm going to take the square root again, and I get 1.79 times 10 to the negative 5th. That's going to be molar. That's my value of x. Now I got to pay attention to what the problem has asked me. It has asked me to calculate the solubility of silver. And notice that the solubility of silver is 3 times X. So I need to take this value here, and let's see, I need to multiply that by 3, don't I? So there we have it. The solubility of silver, which is 3 times X, that's going to need to be 5.38 times 10 to the negative 5th molar. And you know, if I look on the PowerPoint, I see that it asks for the solubility of silver in grams per liter. So we're still not done, are we? I mean, we're done with this problem that as I've written it here, but not as it's written on the PowerPoint. So let me just take this another step. I have 5.38 times 10 to the negative 5th moles of silver for every liter. And I need to change this from moles to grams. So we just showed a little while ago that 1 mole of silver, that's about 108 grams of silver. Let's do that math. I just got my 5.38 times 10 to the negative 5th already in my calculator, and I'll multiply that by 108. And I get 5.8 times 10 to the negative 3 grams of silver per liter, or I could write that as 0.0058 grams per liter silver. And we're done. All right, I'd like to now attack this problem, asking which of these two salts is more soluble in water. Silver chloride with a KSP of 1.8 times 10 to the negative 10, or nickel carbonate with a KSP of 1.4 times 10 to the negative 7. In this case, both of the salts dissociate in a 1-to-1 ratio of cation to anion. Because both salts dissociate into one cation and one anion, we can simply just look at the values of KSP to figure out which salt is more soluble. You see, with such a small K here versus a relatively larger K here, we see that the nickel carbonate is going to dissociate more. So this larger value of K means that this reaction is shifted further to the right in this case than it is this case. And you'll notice if I take this value and multiply it by 1,000, then I roughly get this same value here. So that means nickel carbonate is going to be about 1,000 times more soluble than silver chloride. Now we can't do the same analysis with this particular problem. The reason why we can't do the same type of simple comparison in this particular case is because barium fluoride dissociates into one cation and two anions, which is different than what's going on with nickel carbonate. So in this case, we're going to have to take a more quantitative approach. So let's do that. Let's use an ICE chart. We don't have to worry about the solid to see how much dissociation we're going to get from barium fluoride. And then we'll do the same thing here for nickel carbonate. Okay, in this case, if we gain a barium, we're going to gain 2 fluorides. So we're going to have X and 2X at equilibrium. And in this case, it's just 1 to 1. So here, now in this case, let's see, KSP for barium fluoride, that's going to be the concentration of barium times the concentration of fluoride squared. So in this case, if I plug this in, I'm going to get KSP is going to be the concentration of barium at equilibrium, which is X, times the concentration of fluoride squared at equilibrium, that's 2X, and that's going to be equal to 1.8 times 10 to the negative 7. Now pay attention here, because 2X quantity squared is not 2X squared, it's 4X squared. It's 2X times 2X. So 4X squared times X, that's equal to 4X cubed. Now down here in the case of nickel carbonate, KSP for nickel carbonate, that's going to be the concentration of nickel times the concentration of carbonate, of course both at equilibrium. So in this case, we're going to write KSP is X squared, X times X, and that's going to be equal to 1.4 times 10 to the negative 7. So I'll go to a separate page to do the calculations here. So remember these two here. Okay, so for barium fluoride, I've got 4x cubed. That's going to be equal to 1.8 times 10 to the negative 7. And then for nickel carbonate, we've found that x squared is going to be 1.4 times 10 to the negative 7. Let's run through the math here. I'll divide both sides by 4 here, and I'll get x cubed is 1.8 times 10 to the negative 7 over 4. I need to take the cube root of both sides. 1.8 times 10 to the negative 7. I'm going to divide that by 4, and I'm going to take the cube root of it. Here it is. This is a cube root button. It's x to the 1 over y. So if I hit this, x to the 1 over y, if I do 3, I'm taking the third root of it, which is the x to the third power, so I'm taking the third root of the number. So x in this case is going to be 3.56 times 10 to the negative 3. That's done correctly. So that would be my concentration of barium in water that has some barium fluoride in it. Now let's check it out here with nickel carbonate. In this case, I have x squared is 1.4 times 10 to the negative 7. This is easy. I'm going to just take square root of both sides. 1.4 times 10 to the negative 7. And I'm going to take the square root of that. 3.74 times 10 to the negative 4 molar. So it looks like, just by a little bit, actually quite a bit, by about 10 times, it looks like barium fluoride is going to be about 10 times more soluble than nickel carbonate, according to this particular analysis. So we've shown that on a per molar basis, we're going to get a higher concentration of barium ion than we are going to get a concentration of nickel ion. I just want to push this just a bit further and see in which case will more grams of the salt dissolve. So let's see, in this case I have 3.56 times 10 to the negative 3. That's going to be moles of barium per liter. And remember, X is going to be my concentration of barium that we found. So that's why I'm using this here. But how much of the whole salt in terms of grams will dissolve? Well, let's see. For every 1 mole of barium ions, there must be 1 mole of barium fluoride that must have dissociated. And for every 1 mole of barium fluoride, what is that? Let's see, barium fluoride. That's going to be 137 grams per mole for barium. And for fluoride, that's going to be 2 times 19. Is that 38 and 137? 265. Let's see if I did that right, just to make sure. 2 times 19 plus 137. Oh, I screwed up. Man, did I screw up. Why'd I carry a 1 there? Let's check that one more time. 137 plus 38. I forgot to put, I carried the 1 to the wrong spot. Okay, so that's 175 grams per mole. Good thing I checked. So 1 mole of barium fluoride, that's 175 grams of barium fluoride. So let's see how many grams of the salt would dissolve in a liter. 3.56 times 10 to the negative 3. And we're going to multiply that by 175. 0.623 grams of the barium fluoride salt are going to dissolve in every liter. Let's check it out here for nickel carbonate. In this case, X represented the concentration of nickel. It's also going to be carbonate as well. But let's see. Let's take that as the concentration of nickel. Put this up here so you can see it. Okay, so I'm going to have 3.74 times 10 to the negative 4 moles of nickel in every liter. Nickel ion, I should say. And for every 1 mole of nickel ion, let's see, I'm going to have 1 mole of nickel carbonate. What's the molar mass in nickel carbonate? Let's see, the molar mass of nickel, that's 58 grams in a mole. The molar mass of carbon, that's 12. And then for oxygen, we're going to get 3 times 48. 3 times 48, 3 times 16, which is 48. 48 and 12 and 58. Let's see if I can do the math right this time. 10, 18, carry the 1. Looks like 11 there. Let me just check. 58 plus 12 plus 48. 118 grams in a mole. Looks like it's going to be more grams of the barium fluoride. But let's just see. 1 mole of nickel carbonate, what did we say that was? 118 grams. 118 grams of nickel carbonate. So it looks like, let's see, 3.74 times 10 to the negative 4 times 118.044 grams of nickel carbonate for every liter. So we're going to get more grams of barium fluoride dissolved than we are the nickel carbonate.